So hello, everyone. It's a great pleasure to be here. My name is Jun Paik. I am CEO and co-founder of FuriosaAI. So FuriosaAI, we are building silicon chips natively designed for AI computing with a strong focus on data center inference, large-scale data inference. So now we are definitely undergoing great transformation by AI. AI is about to become far more pervasive than it's today, embedded everywhere across the industries and also in our personal daily lives. You see that the agents are eating the world right now, and we are entering a new era of AI applications powered by frontier models such as Llama, GPT, and DeepSeek, and all these multimodal models. And I also like to emphasize we are also right now seeing a major paradigm shift from training to inference time compute when we scale these capabilities of AI models these days. These kind of powerful new agentic AI applications powered by inference time compute and capable of reasoning, planning, and automating large complex tasks at scale are driving unprecedented demand for compute. And for example, like last March, OpenAI CEO Sam Altman jokingly tweeted that their GPUs are basically melting from the load of generating these Ghibli-style images people are using. So now imagine the scale of inference we need moving forward. And the question is our infrastructure really ready? When you look at the massive CapEx investment plan from these big tech companies these days, and all these kind of new waves of sovereign AI initiatives, we are right now forecasting we need to build dozens to even hundreds of gigawatt scale data centers in like the next 5 years. And actually this summer, Korea hit a new high temperature this summer. And as the result, the total national energy consumption reached a peak of almost like 93 gigawatt. And to put that in perspective, like 100 gigawatt means like total like energy consumption the industrialized nation like Korea needs at its peak time now. And if you think about how we can generate and supply this energy in short amount of time, will be a very challenging thing to do. So our mission is quite clear. Our goal is to make this AI computing more sustainable. Here, sustainable means we are kind of more fundamentally energy efficient. When you say sustainability, it's not just about economics, the environmental sustainability, but it also means the economic sustainability of this entire AI ecosystem. If it costs too high to run AI, the business model of AI just will not work out. And actually, a lot of AI companies are losing massive amount of money due to this infrastructure cost these days. So in analogy, like as we are making a big transition from electric car to from the gasoline car to electric car in transportations, we need the same kind of transformation in AI computing toward a more sustainable and efficient future. Uh, we definitely called for. Okay. So it definitely this transition called for breakthrough technology and product. And here comes Renegade. I brought the real chips here. It's Renegade. And I'd like to briefly explain the major specs of this chip. So the Renegade provides quite robust performance of 512 teraflops of floating point 8 bits, along with almost 1 petaops of integer 4 bit. Also another important spec is this memory performance. These days, memory performance is a key determining factor of our overall end-to-end performance of modern LLM workload. So we are providing a quite high compute-to-memory ratio, and it's providing almost like 1.5 terabyte per second of memory bandwidth. But the most notable feature here is the power consumption. So the Renegade is consuming 180 watt compared to the equivalent performance, the GPU of equivalent performance, which consumes above 300 watt. If we translate this power to cost, we can say this 1 watt saving actually leads to $20 savings per year. So if you save 100 watts, you can save 2,000 watt per year. If you operate like 3 years, it will be $6,000 over the 3 years. If we are thinking about this like 100 mega data center, it's more dramatic. Actually, if you save 100 megawatt, it's actually almost $10 billion over the 5 years. So this energy saving is actually translate to huge saving in the overall cost of running data center AI, along with all this saving these emissions. So to achieve this kind of ambitious product, we are definitely using the most advanced semiconductor technologies. So we are working with the TSMC to build this chip using the TSMC is a 5 nanometer node. We are working with the memory vendor like SK Hynix to integrate the most advanced memory into our chip on top of our core architecture. So it's almost like packing 40 billion transistor into this large SoC die. So it's using the state-of-the-art semiconductor technology, and the benchmarking, the real benchmarking under the usage scenario, the real usage scenario. These days, there is a very golden standard of measuring the AI efficiency, which is tokens per second per watt under the real usage scenario. And we are proving that, we are showing that we are outperforming H100 almost like 190% when running this LLM workload. But I like to, but more kind of into the technology, so how we enable this kind of efficiency with our innovations. I like to elaborate on this efficiency like further, and what's the challenging part of achieving this efficiency. Actually, this especially inference efficiency doesn't just come from actually hardware, but it also comes from the software and the algorithm efficiency. If you see the recent kind of all the innovations in model architecture, like MOE, and also software optimizations, like let's say continuous batching, in-flight batching, and the page attention, and also quantizations. Actually, all these innovations are put together to achieve the overall efficiency. So let's say you design your hardware very locked in a certain set of this optimization, but not flexible enough. Then your hardware will not be able to reflect the latest innovation, and your overall efficiency actually will be worse than actually the GPU approach. So we need a very fundamental architecture that can achieve both efficiency at the same time providing good enough flexibility to accommodate all these future innovations. So this needs quite kind of robust kind of foundational architecture, and this needs a quite holistic approach of a co-design, both like algorithm and the hardware and hardware architecture and the software. So we call our architecture Tensor Contraction Processor. I'll explain a little more about Tensor Contraction Processor, but the Tensor Contraction Processor, through the Tensor Contraction Processor, our goal is to hit a good sweet spot of high performance and high efficiency, at the same time good flexibility. So one of the reviewer kind of described with a hit definitely here a good sweet spot of being generalized for many tensor-based workload, yet specialized enough to exploit many parallelism in modern AI applications. So what is then tensor contraction? Tensor. So in the first place, when you look at AI workload, we know that it's computing perspective is more like matrix multiplications, large-scale matrix multiplications. But more technically, correctly speaking, it's actually tensor contraction computing. Almost like 99% of AI workload, for example, like a BERT-like model in transformer is composed of this, it can be described by these tensor contractions. So tensor contraction is actually much more generalized and flexible, generalized multidimensional matrix multiplication. And the issue with current hardware approach is that they are using kind of fixed set, like a 2D matrix multiplication as a primitive. Compared to that approach, our hardware takes this entire tensor contraction as its fundamental primitive, so that it raises the abstraction of a hardware to a kind of much higher level to support this entire tensor contraction kind of as a primitive. And this provides, this is a kind of fundamental innovation in abstraction, and it provides a huge benefit. So we can take a much more holistic approach of the optimization in energy, and also we make this software development a much more tractable problem. It turns out, as you probably know, this making matrix computing efficient is a very NP-hard problem. It's quite an intractable problem. It's why there are so many efforts to make it more efficient from engineering resource-wise. So raising this abstraction higher and providing the right abstraction to make this software stack much more streamlined gives us more fundamental innovation to provide both performance and flexibility. So lastly, I like to say this chip is already, we are sampling with an enterprise company globally. And we are very excited about application running on our appliance across these verticals, actually. like manufacturing, life science, and energy, and also like a public sector, like sovereign AI. And we really urge every enterprise company to control and own their AI stack, including this computing layer. If you don't control this layer, you depend too much on, let's say, the other solutions, then your cost will be also not controlled. And we try to provide the right solution there to those companies to control their own AI stack. So we have been doing this for the last 8 years, and this is Renegade is our second-gen product. We are still just a startup company, and we are based in Korea and Seoul. The last 8 years has been very exciting journey, also very challenging journeys, but we have quite a high ambition, as I mentioned, like to innovate and be one of the leader in this AI computing space. So thank you for listening. If you'd like to know more about us, please come visit our booth. And we definitely like to work with your team. Thank you. Yeah.